Hi everyone, welcome back. So in the past few videos of the series, we looked at LC oscillators and before that we did ISF model and also limit cycles. So in this video, we'll continue and take things a little bit further. So this one will be a little bit short. So in this video, we're going to discuss, LC oscillators from the perspective of a nonlinear model, sort of a generic nonlinear model. Okay, let's get started. So maybe I would say prerequisites before you watch this video would be to watch MMIC 04, where we talk about limit cycles. What is a limit cycle? What are the conditions for a limit cycle? What it really means. And you really need to know that to understand oscillators from a theoretical point of view. So definitely watch that. And I would also recommend watching the video on cross-coupled LC oscillator. So just an LC oscillator in general, or the cross-coupled video where we discuss the startup condition and small signal sort of analysis for the startup condition. So we'll kind of take that forward in this video. Okay, so just to quickly recap, in that video we said, so I'll say this is the linear negative resistance model, right? Okay, so we said something like, okay, given some kind of an LC oscillator, I have an inductor, a capacitor, and the associated loss, which can be modeled as a parallel inductor in a narrowband case or narrowband scenario. And then there's also like some kind of an active network out here, right? So some kind of transistor. So in cross-coupled case, we saw that it's a cross-coupled pair, but I mean, there are other kinds of oscillator topologies like Colpates and Hartley and things like that, right? So you always have some kind of an active network here. So this is a very high level view of an LC oscillator. Excuse me. So in that video, we said for at least the startup condition, we can model this as a small signal circuit, which is just the same thing. And then this active device could be modeled as negative resistance, as minus R, where this minus R we found to be -2/GM, right, with the transistors. So here you have R, L, and C again. And we said that, okay, this is good enough for the startup condition because in the beginning, the signals are small. But of course, this is not really valid for large signal analysis or steady state analysis of an oscillator, right? And in fact, I would actually say it has some issues, right? So if you watch the limit cycle video, in the limit cycle video, we said that, okay, electrical oscillators that we care about, that we try to design are all basically, they all have some kind of a limit cycle behavior in the state space or the phase space or phase plane. And we said that, linear model, this is a linear model, right? Because this negative resistance here is a linear resistance. And it's a linear model. And therefore we said that, okay, if it's a linear model, you cannot generate a limit cycle. And then we kind of covered that in the limit cycle video as to why it cannot generate a limit cycle. So if you don't know why that is, you should definitely watch that. Okay, so we said that limit cycles require, so you can only find limit cycles require second order differential equation or a second order system, and it must be nonlinear. Second order nonlinear system, right? So in this case, it's second order already because you have an L and a C, and you can specify the current through the inductor and the voltage across the capacitor separately. That's what makes this second order. You can also write the differential equation for an LC network, and you'll see that it's a second order differential equation. but it's not nonlinear, of course. It's linear, right? Because all these components, all of these guys are all linear. So it clearly cannot generate a limit cycle. But we said in the previous video that this is good enough for, we said, but it is okay to study the startup condition, right? So if you want to know if there's enough power basically or enough activity in this active network to get the oscillator going, right? The noise can be amplified and can oscillate. But of course, it's not good enough to actually study the dynamics, right? So in today's video, we'll look at the extension to nonlinear case. So how do we actually, this is a more rigorous or a deeper, it gives you a deeper understanding of where exactly the oscillation is coming from, right? It's not really coming from these guys. It's actually driven by this guy, and that's what we'll see. Okay, so nonlinear negative resistance model. And the reason I put the negative resistance in quotes is that the meaning of negative resistance kind of goes away when you look at a nonlinear case. Anyway, we'll see what that means. So, okay, what is the most general way to think about a resistance, right? So if I have a voltage and a current relationship given by V equal to F of I, and that happens to be IR, then this R is called the resistance, right? If the voltage and current have a linear relationship, then the slope of that linear relationship is called the resistance. But this F need not be linear, right? You could, in fact, in reality, it's not linear. So I could also write this as, I'll call this F1, F2 of V, which is V over R. It's another way to write the same equation. And this F2 here is also linear because 1 over R is just a constant, right? And if it's a negative resistance, then this would be minus V over R. So the IV relationship would be that, which implies that F2 is F2 of X is nothing but minus X over R, right? So in this kind of relationship, if you think of this current source, this as a current source that's voltage controlled, right? So this is a voltage controlled current source. When the voltage controlled current source is a linear current source, then it's like a resistance, but it doesn't have to be linear, right? So for example, I can make it more general. I can say F3 of V, where F3 of X is nonlinear. So when it becomes nonlinear, I mean, a trivial example of that would be if I is equal to V plus 3, right? This is actually not linear. You can try superposition for this and it doesn't work. But in this case, there's no meaning to say that there's a resistance here, right? Because the resistance is only applicable when you have a linear model. And that's why I say, the negative resistance in quotes, right? It's essentially a nonlinear voltage controlled current source. That's the right way to think of it. Okay. So what kind of function do we want this F3 to be, right? So it should have a couple of properties to be sort of more realistic in terms of electrical circuits, right? So the first thing is F3 should be an odd function, right? Which means that F3 of minus V should be equal to minus F3 of V. And that makes sense because if you flip the voltage, you want the current also to flip, right? This is nothing but minus I. So that makes sense. And then you also want F3 to have some kind of limiting behavior. Right? So for example, you make the voltage very large, you make it infinite voltage, the current should not be infinity, right? It should kind of saturate at some point. And you also want F3 to be approximately linear for small voltages, right? So basically F3 of X should converge to minus X over R when X goes to 0, right? That's the mathematical way of saying this. Essentially, we want this to show up when the value of x is small, right? So that's a reasonable, these three are some reasonable properties to expect from this f3 function. Okay, so I'll just take an example of such a function. So f3 of x is equal to the hyperbolic tangent tan h of minus x over r, right? So if you take the Fourier series, not Fourier series, or Taylor series expansion of this, right? So what's the Taylor series expansion of tan h? So tan h of x is equal to x minus x cubed over 3 plus 2x to the 5 over 15 plus some order to the 7, right? So of course, this satisfies all three conditions. It's an odd function, right? And we'll actually see, if you plot it, you'll see that it has limiting behavior. And of course, when x is very small, as x tends to 0, this converges to x, right? So converges to, or I should say, approximately x, or x tends to 0, right? So it has all these properties. And if you actually plot the function, which hopefully most of you have seen before, so x versus tan x, tan h of x, right? It looks something like this. Sorry. Right? And then of course, f of x equal to minus x looks like that, right? So very close, and this is a good example, but in reality, so let me just put a note here. So this is the function I've taken. I've taken a specific example of tan h, but in reality, f3 must be derived from the large signal IV characteristics of the active network, right? So, but in this case, we don't really care. We just want to get some qualitative idea of where exactly the limit cycle comes from, right? Or does it actually produce a limit cycle? To get that kind of intuition, we're not trying to actually make a CAD tool or an analysis tool that's very precise. So that's why I'm going to go with this tan H model, right? Okay, so let's actually do that and see what happens. So let's say I go back and say, okay, I have this kind of, let's do it on a new page. Okay, so I'll say I have my RLC. Now I have the voltage controlled current source. I of S is equal to, maybe I should put it in a diamond. And I of S is equal to tan H of minus V. I'm just setting R to 1 for simplicity, but you can change it if you like. Okay, and then we'll say this is R, C, and L. I'll call this current IL, this current IC, this current IR, and this is obviously IS already, right? And the reason I set this direction for IS is that to be consistent with the resistor, right? So when you define resistor as IV, in terms of a voltage control current source, the current direction should be set like that. You can set this to ground, and I'll label this to be voltage V. And now we write down basically the different equations for this. So it's fairly straightforward. So I'll just go through it quickly. So that's for the resistor. And then for the inductor, we have L DIL over dt. And then for the capacitor, you have IC is CdV over dt. And lastly, for IS, is tan h of minus v, right? So then what we can do is we just expand these out and write a single equation. So I'll say v equal to L d over dt of IL, and IL is nothing but minus IS, minus IC, minus IR, right? So I can put the minus out and I can write this as IC plus IS plus IR. And I have an expression for all three, right? From this, and this. So I substitute those things in, and then let me actually do it. d over dt times tan h of minus v plus v over r plus c dv over dt. Okay. And then this can be simplified, of course, as L times 1 minus tan h square of v. So you take the derivative. That's what you should get. And tan h is an odd function, so I can pull the negative sign out, right? Times dv over dt minus 1 over r dv over dt minus c d square v over dt square. Okay. And I can rewrite this as v double dot, which is the second derivative with respect to time, LC plus v dot times tan h square of v plus 1 over r minus 1 times L plus v equal to 0. Okay, so this is our nonlinear differential equation now, right? So this is a second order, of course, because of the two dots. Second order, and it's nonlinear, of course, because of the tan h part. Not just that, but it is nonlinear. That should be pretty obvious. Nonlinear differential equation, which means it may, or can, I should say, can give, or let me rewrite that. So, which means that limit cycle can exist. It is not guaranteed, of course, but it could exist, right? So now what we want to do is to numerically solve or find the solution to this at different points and see if a limit cycle does indeed exist. So how do we do that? Okay. So I'll say, okay, x, I can write as, I'll say x equal to v, let x equal to v, and x dot, which is v dot, equal to y. Okay, so since it's a second order differential equation, you can write it as two coupled first order differential equations, and that's kind of what I'm doing here, right? So the two coupled equations would be x dot equal to y, and y dot, which is now x double dot, which is this equation up here, I can write as minus x dot times tan h square of x plus 1 over r minus 1. All of this is divided by c minus x over LC. Right, so there we have it. We have our two coupled first order differential equations, and we will use this kind of when we do in the future videos, when you go deeper into oscillator theory, we'll use these kind of coupled first order differential equations to analyze them. Okay, so now that we have these equations, all we have to do is plot the phase portrait or the phase plane or the state space, whatever you want to call it, and see if we find a limit cycle, right? So let me actually do that. Okay, so to actually plot the phase portrait, I've downloaded this function from MATLAB. It's not by MATLAB, it's by, I think, Uzang. It's called plot pp. It's called plot pp. Basically, you can go and download these functions, or you can download it from here. And I made a couple of small modifications. So the modification that I made is that if you open this, I've essentially just also sent in the limits, x and y limits of the plot as arguments to the function. And then I set them over here in line 59 and 60. That's the only change that I think I've made to the whole code. Okay, so what do I have here? I have RLC values. I've set R equal to 2. You can set it to 1, but it's easier to see things when R is 2. The limits of the phase portrait I've set to 5, -5 to 5. Everything is normalized here. Of course, you can change the LNC values to whatever you like, but keep in mind that when you change the LNC values, the y-axis will change dramatically, right? Because what you want to plot is voltage and current actually on the x and y-axis, and when you take the derivative and the frequency is very large, then that x dot axis has to be scaled by the frequency to make sure it's not weirdly warped. But anyways, if they're 1 and 1, it's okay. So and that's, we can look at the normalized case here, so should be fine. And here I have the expression from the notes. So you have x dot equal to y. So x and y here are x of 1 and y of 1, x of 1 and x of 2 in the vector x. So here x of 2 is y. And that's what I have here. And the second equation is this one, which is exactly the same as what I have here, right? So you put in these equations, and then all you want to do is plot the phase portrait. So you run it. And then if you look at the phase portrait, which is this one, we see some interesting behavior, right? So we see that sort of around here, things are going out, right? So these phase portraits are kind of, or these lines, these contours are going out, whereas the contours on the outside are all swirling in. And somewhere in this region, they're all kind of converging onto a single contour, right? And that contour is exactly the limit cycle. So this is not exactly a proof for the limit cycle. You can actually even prove that this is in fact a limit cycle. So the way to do that is to, we reduce this and we take a look. And now we see that all of these, when we zoom in, we see that all of the contours are leaving the space, right? So we found one region on the inside where everything is leaving. And then obviously when if we look at the large behavior, now everything is coming in, right? When we take when we increase the limits to 10, we see that all the contours are going in. So there's a theorem called the Poincaré-Bendixson theorem. A corollary of that theorem says that essentially if you don't have any fixed points in a given space, and then you have an inner region where all the contours are leaving and an outer region where all the contours are entering, then there must be a limit cycle in that space. And here we see that there is indeed a limit cycle, right? So that's the limit cycle. So that's basically it. So what we did in this video is that we said, okay, if I take a nonlinear model for my LC oscillator and I write down the differential equations, and then I write it in terms of coupled 1D differential equations that are nonlinear, and I plot the phase portrait, you can actually see a limit cycle, right? And that's exactly what the oscillator is. And we'll explore, we already did kind of look at the ISF model in the previous videos where we make use of this limit cycle notion a lot, right? And that's really the core of oscillator theory, is to understanding limit cycles. Okay, so hopefully that's an interesting video. You kind of, in this video, we get a good idea of where exactly the limit cycle is coming from. And having that intuition is actually very powerful when you try to understand oscillator theory. So hopefully that was useful, and I'll see you in the next one. Thank you.